Hello everyone. So this is the beginning of another topic called complex numbers. So we're going to start learning about complex numbers from this video. So this would be an introduction to complex numbers, where it came from. So before we begin with the discussion, let's go through some of the numbers that already exist, some of the numbers that you already know of, right? So we'll start with this number set of counting numbers denoted by capital N, set of counting numbers 1, 2, 3, 4, and the list goes on. So when ancient time, when the life was very simple and the math was also simple, people only wanted to count things, right? A number of children, a number of apples you have, a number of things you have. You just wanted to count things, that's it. So the math was also simple at that time. So you gave certain symbols, right? So if you have just one of a certain thing, you gave a symbol as 1. If you have 2 of the same kind, this is a symbol given. 3 of the same kind, this is a symbol given, right? So, and the list goes on. You wanted to just count things. So later on, people wanted to use a symbol to represent emptiness, nothingness, nothing of the same kind, right? So what is the best number that represent nothingness? It's only just one number, that is 0, a big O, right? So later on they included 0 into the counting number set, and they call it a whole number set. So this is the set of whole numbers denoted by W. Set of whole numbers will be 0, 1, 2, 3, 4, and the list goes on. Right. So with time, they wanted to represent deficiencies, right, or differences and negativity. So to represent negativity, they used the same numbers, but they use it with a negative symbol. You know the symbol to represent negativity. This is negative deduction. So they just use the negative part of these numbers and put them all into just one set and call it set of integers. So set of integers denoted by capital C. It goes from negative infinity, then -3, -2, -1, 0, 1, 2, 3, the list goes on, right? Negative, positive, and 0. So this is 0, these are negative integers, these are positive integers, right? So and then with time they wanted to divide things, right? Suppose you had a pizza and you want to divide it among 4 people, right? You want to divide it among 8 people. So what fraction of the pizza you get when it is divided into 4 pieces or 8 pieces? So to represent fractions and all, they had to invent another number system, because they couldn't use this number system. So that number system is called the set of rational numbers, right? Set of rational numbers. A rational number is a number that can be represented by this form, where both m and n are integers, and make sure that n is not equal to 0. Suppose 1/4, 1 pizza among 4 people, or maybe 2 pizza among 8 people, right? This is a rational number. So this is called the set of rational numbers. So a rational number can be represented by a quotient of 2 integers. So that's how we define rational numbers. Then life got very complicated. People start building structures and all, and the circles and different shapes of geometry were introduced, and with this we had this the advent of square roots, right? Square roots of numbers, surds, like root 2, root 3, they are all surds. And also pi, right? Pi was invented, it came with the circles, right? So pi, so these numbers, pi, root 2, root 3, and exponential, you remember exponential? So base is e, this is around 2.7 or something, close to. These numbers cannot be represented like this. They cannot be represented as a quotient of two integers. So that's also a different number set. If we cannot use this definition, then we have to come up with a different set of different definition for them. So these numbers pi, e, root 2, root 3 and all the thirds, they are called irrational numbers, right? They are called irrational numbers, right? So you can see the development of the set throughout the ages, right? Then if you combine this and this, if you combine rational numbers and the irrational numbers, you get all real numbers, right? So up to now you are familiar with real numbers. You have been using real numbers daily. Real numbers encompasses all the sets here, right? Right? All the sets together build the real number set. So the mother of all the numbers is the real number set. That's what you know. But imagine this. Now, this is the first set they came up with. At the time they came up with, they said they didn't know about real numbers. They didn't know about irrational numbers. I don't think they thought that one day we would invent another number system, right? Which is much greater than this counting number set, right? So when it comes to real numbers, they might have thought this is the end, right? But fortunately, there's a bigger number set than the real numbers, that is called complex numbers, and this is what we're going to study, right, with this unit. So the complex numbers denoted by capital C, it's kind of a weird number, old English letters, capital C, and this is called, this set consists of numbers. It's a certain number, it's a combination of a real number, one of these, and another special number called imaginary number, right? It's a combination of these two because they don't mix with each other. You can't add apple and oranges. If you add 5 apples and 3 oranges, the sum would be 5 apples and 3 oranges. You can't say 10 apple oranges, right? No, that's not the thing. So real and imaginary numbers, it's a combination of real numbers are called complex numbers. We'll get to what this is. But I have to give you the notations, the symbols that are used in these set notations. That's why I mentioned complex numbers here. Right. So this is the introduction to the complex numbers and how the number systems have developed throughout the time. Right. So why complex numbers? Where it came from? Where it come from? So here's the thing. When it comes to quadratic equation, you saw that there are 3 types of roots to a quadratic equation. There can be, right? So a particular quadratic equation can have 2 distinct real solutions, or coincident real roots, or non-real roots. So I told you that when it comes to non-real roots, we didn't work with it that much under quadratic equations. But I told you guys that there's a separated chapter dedicated to non-real roots. So these non-real roots are called complex roots, right? You can see complex part is there. So complex roots means the roots built up on complex numbers, right? The roots built up on complex numbers. So where it came from? Came from quadratic equation. So we'll study the simplest quadratic equation here. So you can say that x squared plus 1 is equal to 0. So you know by heart that this can never be equal to 0. Why? So if you look at the graph, this is y equal x squared, y equal x squared, right? So if I get another graph, y equal x squared plus 1, right? So y equal x squared graph, it touches the x-axis. It touches the x-axis, y and x. At this point, it touches the x-axis, which means it has roots, right? So what about this? X squared plus 1, which is exactly what we have here. Y equals x squared plus 1 does not touch the x-axis. It doesn't even touch it. So can it cut the x-axis? No, not at all. What does that mean? It means this will never be equal to 0, but we have this equation. We are forcing this function to be equal to 0, but it won't, it is not equal to 0 in the real world. It's not equal to 0 in the real world, you can see here. If it cuts it, that means this function will be equal to 0 for certain x values. So those x values are real x values, right? That's why we call them real and distinct, real and coincident, and null, right? So this equation will not or cannot have any real solutions for x. It's a quadratic equation. We'll see why. Now this is the graphical approach to it, and to justify that this will not have real solutions, but we can just go about and solve the quadratic equations as we usually do. So what I'm going to do is I'm going to take this 1 to the other side and it becomes minus 1. There it is. So you know that any real numbers are the ones that you know of, right? You don't know any other numbers just yet. After this you would know. So any real number squared gives you a positive number. Any real number, say a is a real number, a squared will always be greater than or equal to 0. So a squared will be equal to 0 if a is 0. Otherwise, it will always be greater than 0. Now, this doesn't make any sense. So what does that mean? X cannot be a real number. X cannot be a real number. So what does that mean? X cannot be a real number. That's what it means. It cannot be a real number. So you don't have to write this down because I just use it for illustration purposes. X cannot be a real number. Let's just go ahead and solve this and see once and for all what we get. So if you solve it, to solve for x, we have to take the square root on both sides. So it be plus or minus negative root of negative 1. Root of negative 1. So what is it? X cannot be a real number. If x cannot be a real number, then it should be an imaginary number, because what is not real is imaginary. So they went ahead and gave this a name. So root of negative 1, they gave it a name as simple I. Simple I, right? So this is called imaginary unit. Imaginary unit, right? So I is the basic unit of imaginary numbers. So we know real numbers. This gave birth to imaginary numbers. We'll see what imaginary numbers are. Now you can see this is the basic unit of the imaginary number. They went ahead and gave this a name. Name is I, right? So I is obviously not a real number, so it must be something else. So they call it imaginary number. So I is the imaginary unit. Imaginary means it's the basic building block of imaginary number. Just like 1 is the basic unit of real numbers. I is the basic unit of imaginary number. So this is called imaginary unit. Right. So we'll look at some examples now. Now, how do I? Let's say I want to solve this one. X squared plus 9 equals 0. Then x squared is negative 9. X is square root of negative 9, plus or minus. So what I'm going to do now? I'm not going to go ahead and give it a name, right? That doesn't make any sense, because if I do that, I will definitely run out of the alphabet, because we have only 26 letters, right? So there are infinitely many numbers in this universe, so we will run out of it. So what I'm going to do here is that I'm going to be smart and represent this quantity using imaginaries. What I'm going to do, I'm going to use laws of indices. So plus or minus, I'm going to do this 9 into negative 1, right? 9 into negative 1. So plus or minus, this would be root 9 into negative root of negative 1. Root of negative 1 is I. Root of 9 is 3. Root of 9 is 3. So the answer is plus or minus 3i. Plus or minus 3i. And always see that you have I. I is multiplied by a real number. 3 is a real number, right? I is multiplied by a real number. Now this one, 3i, is called an imaginary number. 3i is an imaginary number. Is an imaginary number. 3i is an imaginary number. So this is the imaginary unit, and any multiples of imaginary unit is called an imaginary number, or pure imaginary number is a pure, right? It's called 3i is a pure imaginary, perfectly imaginary. Okay, we'll some examples as to how to convert roots of negative numbers how to represent root of negative numbers in terms of basic unit. Right. So this is easy. How do you represent this in terms of I? You have a negative number inside the square root. So negative root 13. So what I'm going to do is I'm going to use the laws of indices to separate this out. Right. Negative 13 is 13 into negative 1. So I separate it out. Now this is our basic unit, 13i. Okay. Then this one, square root of 9 by 4. I'm going to separate it out. 9 by 4 into negative 1. So what about this? Square root of 9 divided by square root of 4. This is I. Square root of 9 is 3, square root of 4 is 2. So you can see that always when you convert square root of a negative number, when you represent the square root of a negative number in terms of an I, it would be a multiple of I, right? Multiple of I. Okay, so this is 3 by 2. Now this part here, this part is a real number. So 3 by 2 is a real number. But this real number, when it is multiplied by the imaginary, it becomes a pure imaginary number. So note here, this one is real, it's a real number, and this one imaginary unit. This one a real number. This is our imaginary unit. Right. So in general, 8 times I, where A is a real number, is called a pure imaginary number. Right? It's called a pure imaginary number. Okay. Right. So we'll discuss some useful results of powers of I next. Right. So this would come in handy. Useful results of I raised to n. I raised to n, where n is integer, where n is an integer. So we could say positive integers. So okay, if it is a negative integer, it would be a division by an imaginary number. So we didn't get to division yet, so let's stick to this. But it works for any integers. Keep that in mind. So I raised to 1 is just I. So what about I raised to 2? I squared means I squared I raised to 2. So what is I? I is root of -1. When you square it, you get -1. So you can see I is imaginary. It's the imaginary, it's the basic one. But when you square it, you get a real number, -1. Right? Real number, -1. What about I cube? Now you should be able to rewrite this using laws of indices. So I can write I into I squared. I into I squared. I3 is I into I squared. I squared is -1. So this would be -I. I minus 1 -I. So what about I squared? Sorry, I raised to 4. I raised to 4 is I squared raised to 2. I squared is -1. So when you square any negative number, you get a positive number. This is +1. So let me just write 1. Okay. So I minus 1 minus I 1. Can see. So this pattern repeats. Let me show you. I raised to 5, you can write it as I raised to 4 into I. So what do we get? I raised to 4 is just 1. So 1 times I, 1 times I is I. If I do one more, I raised to 6, this is just I raised to 2 into I raised to 4. I raised to 4 is 1, I raised to 2 is -1. So the answer is -1. This is actually equal to what? I squared. This is actually equal to I squared. So this thing repeats. So please keep in mind, whenever you come across these numbers, then you can replace them using these results. So you don't have to memorize this. All you need to know is that I is root of -1. If you square it, it becomes -1. Then this pattern will come up, right? Okay, we'll see some examples of this. Right, so let's look at this one. I raised to 10. So write it in terms of what you know. I raised to 10 using laws of indices. I can write it like this. I squared, you know, raised to 5. Right? So what is I squared? I squared is -1. -1 raised to 5. This is an odd power. So if you raise -1 to an odd power, you get -1. Okay. Next, this one. I raised to 21. So you can write it like this. I times I raised to 20. I times I raised to 20. So I raised to 20. You can write I raised to 20 as I squared raised to 10. I squared is -1 raised to 10. So now here this is an even number. So -1 raised to 10 would be +1. So I into 1, that gives you just I. So you can see I10 is -1. I21 is just I. So they they just go around these values. I minus 1 minus I plus 1. I minus I, sorry, let me write it like this. I minus 1 minus I plus 1. You didn't see, sorry about it. So I goes like this. I minus 1 minus I, then plus 1, then it comes back. Right? So I arrange it in this order, in this configuration, because we will see how to represent a complex number, the representation of a complex number. In Cartesian, it's something similar to Cartesian plane. So we don't call it Cartesian plane because we have real complex numbers there. So if we represent complex numbers in something let's call it a complex plane. So we will have different axes, real axis and imaginary axis. So you would find imaginary axis in the word imaginary numbers on the vertical axis and real numbers on the horizontal axis. So that's why I made this configuration. You don't have to take this down as a norm. So we'll get to it later. So far we've seen real numbers and we have seen imaginary numbers. So now our number set has been extended to a larger set, right? So real numbers and imaginary numbers, can we combine these two? When we combine these two, we get complex numbers. So let me do an example. Right, you will see. Right, so as I said earlier, I said complex number is a linear combination of real and imaginary numbers. So we'll see what this linear means, right? So you know about linear functions, quadratic functions, it's quite similar to that. So let's solve this, go ahead and solve this quadratic equation. So I'm going to use completing square method and I'm just going to show you the discriminant. Discriminant is b squared minus 4ac. B squared would be 4 minus 4a is 1, c is 5. So this is just negative 16. Less than 0, which implies no real roots. No real roots. Then what sort of roots are they? If they are not real, then what sort of roots are they? So let me show you how to solve this using completing square method. X plus 1 squared, so you get plus 1, so minus 1 plus 5 equals 0. X plus 1 squared, this is just 4. So x plus 1 squared would be equal to minus 4. Now I have to take square roots on both sides. So x plus 1 would be plus or minus root 4, negative root 4. You know that this is, what is this? This is actually plus or minus root 4 into root minus 1. Now when you get used to this, you don't have to do this step. You can just directly write down the answer. So plus or minus 2i. Right? So that gives us x is equal minus 1 plus or minus 2i. So what are the roots? X is equal to minus 1 plus 2i, or x is equal to minus 1 minus 2i. So notice here, so when you solve this quadratic equation, you get numbers like this. So minus 1 plus 2i. You have a real number, you have an imaginary number. Minus 1 minus 2i. You have a real number, you have an imaginary number. So this is a combination. Just like you can't add apples and oranges. When you add 10 apples and 3 oranges, you get 10 apples and 3 oranges, that's it. So when you add a real number to an imaginary number, you get a real number and an imaginary number, the same combination. This is a combination, this is called a linear combination, right? It's a linear combination. Now notice here, this will come in handy later on. When you solve quadratic equation, you answer, look at it. If this is minus 1 plus 2i, then this is minus 1 minus 2i. So this part will not change, this part will not change, but the sign of the imaginary number changes, right? So make a note on that. So let me note the change in sign of imaginary number. Right. So there are two other examples. Here we have two other examples. Pause the video here and solve this on your own and get the answer, and later look at the answer. I'll give the answer in the board. Go through it and find any mistakes and learn from the mistakes. Right. So pause the video here and do it by yourself. Right. So this is the answer. So when you solve this one quadratic equation, you get x equal minus 2 plus 3i, or x equal minus 2 minus 3i. Notice here again, this part hasn't changed, it's the same number, but the sign of the imaginary number changed. right? This is plus 3a, this is minus 3a. Notice here that x is not real. Now, when you solve this one, you get minus 4 minus 9, so that is negative 13 when you take it outside, plus 13. Take the square root, you get plus or minus root 13, not a negative number. So this is the answer. Now, here is the answer, x equal to plus root 13 or x equal to minus root of 13. X is real in this case. So this is not giving us any non-real roots. Okay. So now you can see that you cannot simplify this further. You have to leave it as it is. Now these are called, this is a combination. You combine a real number and imaginary number. So these combinations are called complex numbers, right? So this is the birth of complex numbers. So complex number, set of complex numbers encompasses both real number set and imaginary number set, right? So this is the biggest set we know thus far. Maybe in the future people will, mathematicians will come up with bigger set than complex numbers, who knows. So maybe we will not be alive when that happens.